So, good morning, good afternoon, good evening, wherever you are in the world. This is the ECOMFIN webinar series at ESSEC Business School, and I am Andrea Roncoroni, Director of the Center. So today we welcome Michael Robert Wagner. He's an Associate Professor of Operations Management at the Foster School of Business of the University of Washington in Seattle. And he holds a PhD in operations research at MIT. Michael's research interests span crowdsourcing, machine learning, topics in operations management and operations research, as well as optimization. He has been extensively publishing in top-tier academic journals, including management science, operations research, manufacturing and systems operations management, as well as mathematics of operations research and the European Journal of Operational Research. So today, Michael is presenting a paper on data-driven profit estimation error in the Newsvendor model. Thanks for joining us, Michael, and the stage is yours.
Thank you, Andrea. Thank you for the introduction. Thank you for the invitation. I'm very happy to be here. Andrea was explaining to me that the audience has varying backgrounds. So I'll talk about the topics I'm going to be touching upon today to better position the talk. And before I do that, this is a joint work with one of my colleagues at UW, Andy Siegel. And we've had basically a couple papers together in this topic. So the Newsvendor model is actually a very popular model in operations management. If you're in finance and other areas, you might not have heard about it. I'll explain it quickly in the talk. It's an optimization model. We're also looking at data, data-driven context. So there's going to be a statistical element, an estimation element, and also some perspectives in terms of machine learning. So many different topics are going to be kind of synthesized in this talk today. And before I forget, if there's any other questions during the talk, feel free to interrupt. It's kind of hard to raise your hand. I might not see it, but feel free to mute your microphone and just speak up. That's perfectly fine, in my opinion. And if there's questions down the road, feel free to just contact me. That's perfectly okay. I didn't include my email here, but you can email me, Michael Wagner at University of Washington. Should be pretty clear, pretty easy. Okay, so let me go ahead and get started. So yeah, the title is Data-Driven Profit Estimation Error in the Newsvendor Model. So I mentioned that the Newsvendor model is popular and fundamental in operations management, but you might not be familiar with it. But if you Google it, there's going to be, by last time I did this about a year ago, over 24,000 results related to the Newsvendor. So it is very popular in operations management, study it both fundamentally and using it as a building block for more complex models. And I've seen it mentioned in other areas as well. I've seen some finance papers mentioning Newsvendor. So at the very least, hopefully you'll learn something new about the Newsvendor model in case you haven't learned about it yet, and other aspects about our research related to Newsvendor today. Okay, and I will explain what it is, what the fundamental Newsvendor model is soon. So what we're looking at, I'm going to kind of summarize what our research is. So first, let me just say what the Newsvendor model is. It's you can think of it as a model for maintaining inventory. You have one opportunity to place an order for how many items you are going to have on your shelf. Then demand is realized. And either you have too much or too little. If you have too many items on your shelf, that's going to be wasteful because if they're bananas, they go bad. If you don't have enough, you're going to miss out on sales and there's going to be an opportunity cost there. And that is costly as well, okay? You can either set it up as a cost minimization or a profit maximization, and I'll be doing the latter. So what we're looking at is the situation where you make a decision and the model is telling you you can expect so many dollars in expected profit. We're looking at that and we're identifying a problem. So we're going to have some mild assumptions on the form of the stochastic distribution for demand. I'll mention that a little bit later. But more importantly, we're looking at a data-driven environment. We're starting with a data set. historical data. This is more aligned with how research and scientific models work in the real world. So in this situation, we're going to show that a very natural approach to estimate expected profit is going to be have a mistake. It's going to have a bias, in particular, a positive statistical bias in the statistical sense. And what that means is, if you're applying this model and you're suppose you're a scientist or a quant or a data engineer, say at Amazon, at Google, and you say, my model is going to do this, and we can expect on average $10,000 of profit a month. That's going to be a overly ambitious estimate. And in reality, you might only get 9,000 in expectation over a longer time frame. So what that means is your boss, your manager, is going to be expecting more money, more profit out of your model than is actually going to be realized. And the manager can get fed up and you could be let go or fired. So what we want to do is to figure out a way to kind of overcome this bias and have a more accurate estimate of what the profit is going to be. And that's the main content of what we're trying to do today. Okay, so we're going to provide a correction based on our derivation of the bias that is going to allow us to come up with an unbiased estimate of the maximized profit. So that's the idea. And I'll get into the details so this becomes a lot clearer as we go forward. Okay, here is the Newsvendor. So I'm going to talk about the classic Newsvendor to start with. So if you're not familiar, this is the most fundamental version. We're going to assume that demand, customer demand, call it X, is going to be a continuous random variable with some cumulative distribution function F. The unit cost to purchase one item from your supplier is going to be C, say $10. And the unit revenue from selling to customers is going to be P, say $20. So a huge margin there. And here's a small little optimization problem. Let me kind of dissect it for you. So if we have this expression, min time the minimum of X and Y, the minimum of your demand and Y. Y is going to be your decision about how many units to purchase to stock your shelves. So the minimum of the demand and supply is sales. So you can't sell more than you have, and you can't sell more than the number of customers. So that highlighted expression is sales. If you multiply that by the selling price or the unit revenue, that is going to be your sales revenue. And then we're going to subtract out the cost, the procurement cost of obtaining Y units at a unit cost C. So taken together, revenue minus cost is profit. X is random, so we're going to stick that into an expectation. And this entire expression is expected profit. And we want to choose Y, non-negative Y, to maximize expected profit. That is the fundamental Newsvendor problem. And we're using a continuous demand distribution. If you expand out the expectation into an integral, and then you take a derivative, set the derivative equal to 0, you can get the optimal solution. Taking the second derivative, this is a concave function. So the solution to the first derivative gives a maximum. And that solution, if you go through the calculus, is this answer right here. This expression, 1 minus C over P, the unit cost divided by the unit revenue, that is called the critical fractile. And you're taking the inverse of the demand distribution at that fractile to come up with your order quantity Y star. So that is going to be the optimal answer to the classic Newsvendor. Okay. However, in reality, we typically don't have a distribution. So we're going to look at a data-driven Newsvendor because in reality, what we do have is data. We don't have the distribution. F is not known, but we do have a sample of data. So capital X is a random variable, lowercase x1, x2 up to xn are the realizations. And just think about historical data. So if you don't have the distribution, but you do have data, a very natural approach is to replace what you don't know, the actual distribution, with something you do know. I'm going to call that F hat, and that is going to be the empirical distribution induced by the data. It is a discrete distribution, so a probability mass function. And if you have n data points, this empirical distribution is going to give weight, a probability mass of 1 over n at each of these data points. That is the empirical distribution. And you simply stick the empirical distribution in place of the true distribution in the Newsvendor model. And if you kind of do that and simplify, this is the data-driven Newsvendor model right here. And if you think about it, the x is replaced with xi, and each of those is weighted by the probability 1 over n in the empirical distribution. And you sum over all those realizations of profit, and that is indeed the expected profit using the empirical distribution, which is discrete. So this is the actual model. This is the approximation to it, because we don't know f. This one can be solved as well, not via calculus methods, because this is more discrete. But if you go through the math, and this is something that's been known for a while, we didn't do this, but you can show that the optimal solution, y, and I have a subscript SAA, because this is known as a sample average approximation technique. And the answer is going to be the smallest data point xj, such that this inequality holds. On the left of the inequality is basically the evaluating the CDF at different values of xj. You want that to be at most a critical fractile. So it's the analog of the actual answer. And you can derive this using just going through the math and the optimization. And it can be simplified a little bit more. It's the optimal order quantity is going to be the kth order statistic. So the subscript with a parenthesis around it means an order statistic. And k is this value right there. So that is going to be the solution of the data-driven Newsvendor approximation, known as the sample average approximation. Danko. I think you're muted.
I always do. Sorry. So when you talk about data, I'm assuming that you are talking about sales data.
So here, no, we are assuming that we know demand data, and that is it's a limitation. And we have tried to extend it. It's a lot more difficult, but this is actually going to be demand data. And I will say that that is in line with the literature, which I'll go over briefly in a couple of moments, about assuming that you have demand data. So now I would say if you want to publish something.
Yeah. How would you go about actually inferring demand data in real life? Like, even if suppose you could do it, do you have any idea
There
how
are
you
a couple of techniques. There are a couple techniques for looking at sales data and estimating the demand distribution. So for
like
instance,
uncensoring, I guess. Yeah.
Exactly. You look at the data that is uncensored, that is the case where sales equals demand, and you learn some structure there, and you apply it to the censored data to kind of interpolate, and then eventually you get an estimate of the demand distribution. So various techniques for doing that.
Yeah,
but we don't do any of that. We just assume.
Yeah, but I guess this would not work well on something like data from CompuStat, right? Where it's basically aggregated across stores and.
Oh yeah, no. So we're looking at a very fundamental case, and then if we want to get into more complicated use cases, we view this as a building block, and then we need to do more research to get to the point where we can solve those problems.
Yeah, no, I'm not asking this as a critique. I'm simply asking to kind of, because everybody is in the same, trap basically. And so I wanted to kind of just check. Okay. Thank you.
And there is a way. It's not easy, but it's possible. I'll say it that way. Okay.
Thank you.
Any other questions before I continue? Thank you. Of course. Thank you. Okay. All right, so summary of main results. And if you remember anything from my talk today, it's going to be this slide. I like to do this earlier in the talk when people are have a little more energy. So assume we do this, and we made our optimal ordering decision, YSSAA, based on only data. We want to have an idea what kind of expected profit we're going to get. So what is typically done when you're doing an optimization, including the classic Newsvendor, is you take your optimal solution, stick it back into the objective function, and that's what you can expect to get. So we've taken the SSA, we look at the objective for the sample average approximation, the data-driven Newsvendor, and we simply stick in the answer that we got. And we're going to say that this is going to be our estimate for the expected profit. And it seems fairly intuitive because we're optimizing a model, we find the best variable, we stick it to the objective. But I do want to remind everyone that this model that we're using is an approximation for the true model, and it's the true model expected profit that we are interested in. The problem is we just don't have the F, so we can't evaluate it. So we use the next best thing, approximate model, stick the answer into the approximate objective, and say this is our guess for what expected profit is going to be. However, one of our main contributions is that we showed that this is positively biased. The estimate that you get from plugging and chugging this expression is larger than what the true value is, strictly larger. So the bias cannot be zero. We show that it's positive.
Quick question.
So,
Michael, what if this is either a new business or a business for which, for one reason or another, we have no access to a sample?
Yeah, so that's typically referred to as the cold start problem. If you really have no data for your business, what is typically done is you try to find a similar business that you have access to data. And that obviously might be hard, but if you're looking at a company, if you're starting a new product, a new service, and you have no data for it because it's brand new, you look at something that's been done that's similar. And you might get a set of similar businesses or a set of similar firms, and then you kind of use all that data as an aggregate proxy for the data that you would like for your use case. It's imperfect. It doesn't work nearly as well as if you did have data, but there is a path forward, at least in theory. But we didn't consider that much at all in our paper. We basically assumed we had the data, and that was our starting point, and we went forward. But it is a very relevant question that is encountered a lot in practice. I will say that.
Okay, thank you.
Does that answer your question?
Yeah, thank you very much.
Okay. Okay, so now let's make this a little bit clearer about why we're getting a positive bias in this discrete approximation to the true classic Newsvendor problem. So let's look at it from the random variable perspective. So what I'm going to do, all the X's and the Y's, I'm going to make capital letters because I'm basically going to make it random. Think of this as before we actually randomly draw the realizations from the distribution for the data. So I'm going to call the estimate that I had just proposed as the naive profit. So it's the same exact expression, except the random variable, the letters are capital, so they're random variables now. And I'm sticking that into an expectation with respect to the true demand distribution. So this is the average naive profit. Note that this estimate that we're using is actually the realization of a random variable. So there's going to be some noise there. But even if we take the expectation, it's going to be wrong. One thing I want to point out is YSAA is a function of the data that we have, because that's how we calculated it. That was on the previous page. So it's the optimal order quantity is a kth order statistic. So obviously, Y is a function of the X's. Now, the true profit is this one. Going back to the classical form of the Newsvendor model, I'm using the expectation with respect to F, the YSSA as before, but now I don't have I or N demands. I just have a single demand. But the important difference is Y is a function of X1 through Xn, but the demand in this profit expression is X without a subscript, and we're assuming that X is independent of the data. And if you think about this makes sense because we're using historical data to make a decision today, and then we're going to observe the profit going forward for a new data realization. Your order quantity does not depend on the demand in the profit expression. Another way you can think about this, thinking about this in terms of machine learning, the naive profit is an in-sample measure of profit, whereas the true profit is out of sample, which is what we want. We want to know how this is going to behave in practice with new data, with new demands. Okay? And our main result, our first main result, is showing that the naive expected profit is equal to the true expected profit plus a bias where the bias is strictly positive. Therefore, what we think we're going to get is more than what we're actually going to get in expectation. And everyone, you might be thinking, why not use the true profit? The true profit depends on the true distribution, which we don't know. And that's the problem. We're kind of stuck with this naive profit. So what do we do? And that's the second part of our paper. We're going to see, once we know what the bias looks like, we're going to adjust our naive expression, or more concretely, this one. We're going to adjust it so that it becomes unbiased. Okay. All right. So let me go ahead and get into the details now. Oh, before I do a quick literature review, Danko, you have a question?
No, thank you.
Oh, okay. Okay, quick literature review, and this is most of this is the first set is related to sample average approximation. Use available data to come up with an empirical demand distribution and apply the Newsvendor. So quite a few papers in this space. Recep Levy is one who kind of started this. He's at MIT. Robin Roundy, David Schmois, I think Cornell, Georgia Prakis, MIT, and Jolene. I forget how to pronounce her last name, but she's in Michigan. They have some nice work. They're saying that if your sample size is at least a certain number that's based on problem data, the sample average approximation is going to be within a certain percentage of the optimal with high probability. So very nice results. Gagny Ban and Cynthia Rudin, they kind of extended this to features for the demand distribution, but very similar results. But the problem is, so even though they can, if you do what they say, they can guarantee you're going to be, say, within 5% of optimal, you cannot calculate what that optimal is. You cannot calculate what your expected profit is. So it's an implicit result. You know you're going to do well, but you don't know what the actual numbers are. They're not computable because you don't know the distribution. Similarly, in approximation algorithms, and again, Recep Levy is leading the charge here, a bunch of results with variance, multi-period, capacities, etc. They can guarantee that their solution is at most a multiple of the optimal solution. But again, the optimal solution is not computable. Their solution is not computable because you need the distribution F to calculate the expected profit. And finally, I'll compare with a paper of our own. It's a paper we published a number of years ago. Very similar results, but we assume that the demand distribution has a parametric form. Say it's normally distributed, we just need to estimate the mean and standard deviation. Or it's exponential, we just need to estimate the mean. But knowing the parametric form of the distribution is information, and it helps out a lot. We remove that in this work, and we only have data, no assumptions about the demand distribution, other than it is smooth and continuous. Okay, so now let's get into the meat of the research. I'm going to talk about the sales bias, because if you look at the expression for profit, the procurement costs are the same in both cases, and the unit revenue is the same in both cases. So without loss of generality, to make it a little bit simpler to analyze, we're going to look at the sales bias. Okay. So the naive sales bias is this expression right here, and the true profit, the true sales is this expression right here. And I'm just going to kind of expand them a little bit. This is just algebra. This first expression, you can consider it overage. The overage sales, this is when you order too much. These are all going to be the order statistics from 1 to k minus 1. So these are demand realizations smaller than the order quantity. So you're only going to sell the order quantity in these cases. And in the other case, this is the sales in underage if you don't order enough. So you're only going to sell the order quantity. And you can kind of think about these two parenthetical expressions as the probability you're going to get those two. With a true sales expression, you can use a law of total expectation, kind of split it out in a similar way. And you can notice that there's differences between these two, okay? So the expected sales on the naive sales expression in the underage case is just the expected value of the order quantity. In the true case, it's a conditional variant of that. In the underage case, this is unconditional, and this, on the true case, it is conditional. So you can see there's differences. And the weights, these probabilities, you can also see that they're different. Let's just focus on this last one. The denominator here is n. The denominator here is n plus 1. I'm going to go back to that later in the talk, time permitting, and you can see that they're different. So there's differences here, and that is driving the difference. But we're going to come back to that, like I said. Okay. So now that we have these expressions, I'm going to find the sales bias. It's the expected difference between the naive sales and the true sales. And then we can get the bias profit by simply multiplying it by the unit revenue P. Okay. And here's the expression for the sales bias. The sales bias, the difference between those two approaches, is going to be this expression. We have this component here dependent only on problem data, and is the sample size. We have a little bit of an error, but that's big, that's a little o of 1 over n. That goes to 0 faster than 1 over n. The only problem is this denominator here, f of y star. Y star is the true order quantity for the classic Newsvendor, the original Newsvendor, that depends on the distribution f. And little f is the density, the derivative of the distribution function. So we don't know those. We don't know f or y star, but we can estimate them. But this is the true expression for the sales bias. So before I go into using this bias, let me show you that this is not negligible. So I'm going to show you bias as a percentage of the true expected profit when demand is exponentially distributed with a mean of 200. Okay. So on the left, I have the percentage as a function of n, and this is for CRP 0.6. When you have a small sample size, you have a very significant bias. As the sample size increases, the bias goes to 0. So if you have a bunch of samples, you don't have to worry about this too much. And you might even argue, we're in the era of big data, we have big N for everything. This is not relevant. I would argue that is not true. Take Amazon. Amazon sells, has a lot of data. They're truly big data, but they also sell a lot of different items. If you're looking at a specific item, say a girl's t-shirt for a 5-year-old girl that has blue and red colors, blah, 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 getting very specific for a specific product. If you look into the data, you actually don't have that much data. You might be, and there are cases that I know of, you are in this regime right here. So even though we have a lot of data, we have a lot of products. And when you look at a specific product, you might not have that much data for it. On the plot on the right, we have a reasonable sample size, 25, and I'm varying the C over P. As C over P increases, we have the bias becoming larger and larger percentage of the expected profit as well. So this bias can be significant in many situations. Okay. So now that we have this theoretical expression for the bias, we realize we can't calculate it either because it needs something we don't know, the distribution. So we're going to estimate it. So the true bias is in the first row. We don't know f, we don't know y star. We're going to estimate it. So I'm going to introduce f hat as an estimate of f evaluated at the optimal order quantity y star. Okay. So in the data-driven context, our order quantity is SAA, which is the kth order statistic. And we're going to take a numerical derivative of the empirical distribution to calculate the empirical density. And that will allow us to estimate this sales bias. So this is how we did it. We're going to start at the order quantity. And we're going to use two order statistics on either side of xk. Okay? And we're going to choose ranks k minus m and k plus m for some integer n. The simplest case is the one that we use in most of the numerical studies, is having the two order statistics surrounding xk. So xk minus 1 and xk plus 1. But it's generalizable. And there is some esoteric statistical theory that actually can specify what kind of value of m you want for the best possible results in certain situations. Okay, so if we're looking at the order statistics at ranks k minus m and k plus m, moving from the lower order statistic to the bigger order statistic is going to increase the CDF by 2m over n. And then if we just go back to Algebra 101, the derivative in this case is a slope, change in y over change in x. And we know the x changes from the lower order statistic to the higher order statistic. So our estimate of the slope, or the derivative, at the point y star is simply the change in the CDF value when you move from one of those points to the other, divided by the change in those points themselves. So basically, change in y divided by change in x. That is our estimate. So that allows us to calculate concretely an estimate for that sales bias. And we're able to show that the expectation of that estimate is equal to the true value plus a little error term that goes to 0 very quickly. So that's good enough for us. We're going to use this as our estimate. So to correct the bias, we're going to limit ourselves to only problem data and the historical data that we have. Our adjusted profit estimate is going to be the one I had proposed at the very beginning, because there's nothing much else you can do. And then we're going to subtract out the estimate of the profit bias, which is simply the sales bias multiplied by P, the unit revenue. And this is going to be our proposal for anyone wanting to more accurately estimate expected profit in practice. And we can actually show that the expectation of our adjusted profit estimate is equal to the true profit plus a little error term that goes to 0 very quickly. So that's the theory. We obviously, since we want this to be applied, and we did some numerical simulations to see how it works, and I'll kind of outline those right now. So we're going to take a... Before I continue, are there any questions? Denko?
Yeah, I have a quick question. So I just wanted to make sure that I understand this correctly. So you guys are adjusting the expectation, not the estimate of the CDF.
Yeah, our goal is to estimate the expected profit. In
so
practice,
if I take data and I infer the CDF, and then based on that data, going forward, start making my ordering. My inventory orders going forward, based on my estimated distribution, would be biased. But you can only unbias my expectation in terms of what's going to happen to my expected profits. But you cannot really unbias my ordering.
So the order quantity is optimal. So we're not saying anything about the quality of the decision itself. That's not changing. We're just evaluating the profit in a better way. So the emphasis is not on optimization, it's on estimation.
Right.
So we're not changing the order quantity at all.
That I'm getting out of this is optimal. So if I estimate my CDF from past data, and then I base my ordering based on that going forward, my order quantities are going to be optimal, but my expected profit is going to be biased. Is that what you're saying?
It's optimal, but the naive estimation of profit is biased, because if you look at the very beginning, we have these two models.
I'm sorry, I don't mean to wreck the flow of your presentation.
No, it's okay. So if we have this data-driven Newsvendor right here, the YSAA is optimal, and that is optimal for this objective. But the point
Okay.
is, this is an approximation of the true objective. We claim that the original classic Newsvendor, this is what we want to optimize. And this is the what we want to estimate. The problem is we don't have the F. So we're keeping this fixed. We are not changing the decision making at all. We know it is optimal. We're just we want to understand better what we're going to get from the optimal solution. So our objective is expected profit, and simply plugging this order quantity into this approximate model and thinking that that is the expected profit is wrong.
I got it. I got it. So you guys are not after, so yeah, really, truly after only estimating the expectations going forward based on a given ordering policy.
Exactly. So in the literature review that I mentioned really quickly, these guys, they're looking at different ways of updating the YSSA. We're not doing that. We're just looking at the estimation. So more of a statistical type of project.
Paying close enough attention, but I got it.
It's okay. No worries, no worries. Thank you for the question. I'm sure others benefited from the clarification.
Thank you.
Okay. Yeah. So, all right. So we have our theory. Let's test it out with some simulations. So let me outline how we did our numerical experiments. We decide on a given demand distribution, say it's normal, exponential, whatever. We know the full distribution. And we're going to create a sample of size 25 IID from that distribution. And then we are going to calculate both the true Newsvendor solution and expected profit. And then we're going to calculate the SAA order quantity. And once we have the SAA order quantity, we're going to calculate the naive profit estimate and the adjusted profit estimate. Okay. Once we have all three of those profits, the true profit, the naive profit, and the adjusted profit, I'm able to calculate two estimation errors: the difference between the true and the naive, and the difference between the true and the adjusted. So that is what we get out of step one. We get two errors. We're going to repeat step one 10,000 times to get 10,000 errors for the naive estimate and 10,000 errors for the adjusted estimate. That allows us to calculate the mean errors for both the naive and adjusted. And we're going to test those two means against the null in hypothesis testing, a null of 0 estimation error. And then for the hypothesis test, we calculate two t-statistics. Okay. So if you recall, if the t-statistic is large enough, and think about a threshold of 2 in magnitude, if the t-statistic is greater than 2 in magnitude, you're going to reject the null and say that the estimation error is not equal to 0. If the t-statistic is small enough, we're going to accept the null that there is no estimation error. Then we repeat step 2 100 times to get 100 pairs of t-statistics. And this is to get a nice little visual. So let me explain the plot on the left. The plot on the left is assuming that demand is normally distributed. And the red histogram is the histogram of all the t-statistics for the errors for the naive profit. And we can see that the t-statistics are all at least 22, way beyond the critical threshold of about 2, or 1.96 if you want to be specific. So in all these cases, in the naive profit estimation, we're going to reject the null of 0 estimation error, and we can infer that there is a positive estimation error, so we have a positive bias. The blue histogram is the same thing except for our adjusted profit, and you can see that it is centered around 0. Most of these critical ratios are within the 2, plus or minus 2. And I think a couple are out, but if we're doing the critical ratio at the 95% level, the threshold of 2, that means a few out of 100, we want 5 of them to be outside. So, but the net conclusion here is there is no estimation error for the adjusted profit expression that we came up with. The plot on the right is the same thing for log normal demand. So we have theory and numerical results to support our theory Let's say that if we take a naive estimation of profit, it will be introducing a positive bias with respect to the true expected profit. However, if you use our adjusted expressions are unbiased estimates for the true expected profit. Okay. The other thing I want to mention is our approach actually outperforms cross-validation, another machine learning technique. So what this is in a nutshell, if we have data, say 25 data points, we randomly put aside the first 5, and that's for a testing data set. And then we apply our model on the first 20 data points. We come up with an order quantity, and then we estimate its expected profit on the holdout data set, those 5 remaining ones. And we repeat 5 times where each data set, each testing data set is cycled through a different set of 5 items. So that was a very poor description of cross-validation, but it is something that is well described in machine learning. It's intended to solve the problem what we're doing right now. We want to come up with an out-of-sample estimate. And this is what the referees asked us to compare our approach with to have a better sense of the quality. And we do better. So the red is the same as before, the blue is the same as before, the green is a cross-validated estimation of the expected profit. And you can kind of see that it overcompensates. It introduces a negative bias. In some sense, that's not nearly as bad having a positive bias. The positive bias is much larger than the negative bias. So if you say, oh, we're going to get $95 in expectation, then if you get 100, that's a good thing. But we would argue that our approach still outperforms cross-validation because our estimation error is 0. It's not positive and it's not negative. So the referees accepted that and they were happy with it. And finally, I want to compare our results, our current results that I'm explaining today, with something that we did a couple years ago where it's very similar, except we assumed a parametric form. We assumed demand was normal, but we have to estimate the parameters, and so on and so forth. As I mentioned, when you have the parametric form of the demand distribution, that's a lot of information. So this is the plot to kind of compare. The red is, as before, it's the naive data-driven profit. The blue is as before, our adjusted profit from today. The yellow is the unadjusted profit in the parametric case. There's more information there, so you're not dealing nearly as badly as the current data-driven context. And in that case, we can eliminate the bias as well. But in the current research, we're doing a lot better. We're able to correct a much larger bias. So you can think about the gap in our previous paper as the horizontal distance between the green and the yellow histograms. And in today's talk, the gap is between the blue and the red histograms. So even though we have much more bias to start with, we can do just as well using less information in the data-driven context. Okay. So a couple more things. I'm not going to do all these slides. There's some graphics that'll take a little too long, but I want to dive a little bit deeper and get a little bit more intuition about the sales bias. Where is it coming from? So we're going to decompose sales into overage sales and underage sales. Overage basically means you order too much. Underage means you order too little. So here's the naive profit. I'm splitting it into the first component, which is the sales under overage. Basically, you order too much, so your sales are only driven by the demands. And the second expression is the underage sales. You didn't order enough, so you're only able to sell what you ordered. You're missing out on some of the demand. Doing the same thing for the true case, even though we start with a very different expression, we can very easily do the same thing with indicator functions. The true overage sales and the true underage sales. And we kind of split out the bias from underage and overage. And actually, this is how the theory worked. And what I had shown you previously is basically putting these things together. But in overage, the sales bias is the expression that I just showed. In underage, it's a different expression. And I just want to highlight these red components are the same in the two expressions, except in the first one is negated. So when you add them together to get the overall sales bias, they cancel. And then the final expression that I showed you earlier is just over there. And therefore, we get a little bit of insight, at least theoretical insight, that the bias comes from underage. There's not really any bias whenever you order too much. The bias is always coming from when you order too little. We're not sure what to do with that yet, but it is an interesting theoretical insight about where this bias is coming from. Okay, since I don't have too much time, I'm going to skip these plots. It's basically, we're not losing too much because the referees asked us to visualize the bias. We did, and then they said, oh, we don't like it, take it out. So I don't think we lose too much by skipping it today either. Okay. The last thing I want to mention before I conclude with I think I have less than 10 minutes left, is an extension for discrete demand distributions. If you recall, everything I've done so far was assuming that the demand D and the demand X had a continuous distribution F. What happens when it's discrete? So this is the best we can do right now. So if we take our continuous results and extend to the discrete case, we hit a roadblock because our results depend on a density. A density does not exist in the discrete case. It's a probability mass function in that situation. They're distinct mathematically, so we can't apply our results directly. However, we're thinking about this, scratching our heads, and kind of going through all our results. And in level 10 of our paper, we find this result. The covariance of the order quantity y, I suppress the subscript, with the density evaluated at that order quantity y, is this expression on the right. And that looks very familiar, hopefully. That is really close to the true bias expression, except that here I have the F, the density evaluated at y star, and here it's evaluated at the expected value of the SAA order quantity as a random variable. So a little bit of a difference. So we're not able to do anything with the F, the densities, so we're instead going to focus on the covariance. So we conjecture in the discrete case that the bias, the sales bias, is equal to this covariance. And we did this because the covariance can be estimated in the discrete case using bootstrapping, for example. And I'll show you that in the next slide. But that's the reason we're kind of zeroing in on this covariance, because it's a loophole of sorts to get around not having the density F, little f. So let me show you how we do this. We're first going to estimate, using bootstrapping, the distribution for y, the order quantity, based on data. Okay, so we're going to have this data set, x1 through xn, and in theory, the order quantity y can be any of these. It has to be the kth order statistic. These could all be the same. So in theory, it could be any of these values. So what is bootstrapping? We have n data sets, and in order to estimate the variance or the covariance of, say, y, that's difficult with a single data set because in a single data set, y is one of the values. It's the kth order statistic. However, if you want the variance of y, it's impossible with a single data set. So you create a bootstrap data set. So if you have a data set with n elements, you create another data set with n elements that's created from this base data set with you're using sampling with replacement. So I could choose x1 twice, x2 none, and so on and so forth. And that creates another data set. And I can easily do that 100 times, 1,000 times. Okay. So we want to know when y is any of these values, what is the probability that the order quantity is equal to that y value? So we're going to think about those bootstrap data sets and the probability that any given element, say xi, is strictly less than y, in the bootstrap sample is basically you're going to add up the probability mass 1 over n for all the data points that are less than y. So relatively straightforward to estimate that probability. You can do the same thing with the probability of getting a bootstrap element that's greater than or equal to y, or greater than or equal to y. So less is strict, greater is strict, and then equal is obviously equal. So given a bootstrap sample of size n, you can kind of divide it into 3 groups. You're going to have n less elements that are strictly less than a given y, n greater elements, and n equal elements. And the values of n less, n greater, n equal can vary, but there are some limitations. So remember that y is going to be the kth order statistic. So n less has to be less than or equal to k minus 1 and greater than or equal to 0. N greater is between 0 and n minus k. Equal is equal to n, the total number of data points, minus those 2. Okay. And just really quickly, since n less and n greater is less than or equal to n minus 1, we're guaranteed to have at least y equal to the kth order statistic that we wanted. Okay, so we are able to estimate the probability mass function of y now. So the estimate of the probability that the random variable y equals a given little value y taken from the data set is equal to this expression. In the middle, this is simply the multinomial distribution. So n less items with probability p less, n equal items with probability p equal, and n greater with probability p greater. And this ratio of factorials is simply the multinomial coefficient. It's a simple generalization of the binomial. Binomial, you have success and failure. Here we have 3 classes, n equal, n less, n greater, but it's the same thing. And simply we add up or aggregate over all the reasonable values of n less and n greater. That gives us an estimate for the PMF. Once we have that estimation of the distribution, we can estimate the covariance as follows. So the first component, you're summing over the y values, you multiply the probability times the y value times the f of y value. This is an estimate for the expected product. And then you subtract out the product of the expectations. This is the estimate for the expectation of y. This is the estimation for the expectation of f. And that's how covariance is one of the definitions, is the expectation of the product minus the product of the expectations. And then we have the adjusted profit in the discrete case, the naive profit minus p times the estimated covariance. And to conclude, I'm almost out of time, that hypothesized relationship goes overboard. It eliminates the positive bias, but then it introduces a negative bias. Arguably, that's not that bad, because like I said earlier, if you're expecting $95 but you get 100, that's a good thing. But still, there's a bias, and it basically overshot it, and it's not correct. So we need to do more work for the discrete distributions. And then finally, in the last 2 minutes, let me just wrap up. We looked at the fundamental Newsvendor model with a continuous demand distribution in a data-driven context. We only have a sample of data and no demand distribution. We show that a natural estimation of expected profit, frankly, the only thing you can really do in that context is going to be biased. It's going to have a positive bias. You're going to expect more than you're actually going to get. And we're able to derive it in closed form. So in practice, this will be a problem because your boss will be chronically disappointed, and we want to avoid that. So we're able to take our closed form for the bias expression and come up with an adjusted expected profit expression. We show that it is asymptotically unbiased, and since it depends only on data and problem parameters that are easily available, it can be easily deployed in practice. And to conclude, I'll mention what we're thinking about going forward. We want to figure out the discrete case. We're exploring different techniques because the techniques in this paper just don't work because it's heavily based on the notion of a continuous demand distribution. We're also considering the case of a contextual news vendor where there's going to be features that are going to influence the demand distribution. That's we haven't done that yet, but we plan to. So that's my talk today. I'm happy to answer any questions. I know it's late over in Paris, so if you need to drop them, no problem, but I'll stick around until all questions are answered.
Okay, thank you, Michael. Is there any further question?
Yeah, I have a quick question about are there some policy implications to this other than just expected profit implications?
Policy, can you give me an example? At first I'll say no.
Will this help me manage will this help me somehow make better decisions other than just give me better estimate of what my decisions will generate?
Okay, I would say possibly on the strategic side. So narrowly speaking, in terms of the news vendor, we don't discuss improving decision making at all. We focus only on estimation. However, in practice, on a more strategic front, you could say that, okay, this division, we're doing something that has like a news vendor structure. We estimate we're going to get $20 million of profit. Suppose you only get 17 million longer term. So that shortfall is going to affect budgets, and that might affect future layoffs. It might affect cancellation of future projects. Whereas if you had correctly estimated from the beginning, you won't be faced with a shortfall and having to scramble down the road. So that's how I would answer a potential policy impact of this research.
I see. Maybe also helping me decide whether I want to get into this product in the first place, given particularly ordering policy. But then for those, I don't really have a lot of data, right? So it might be hard to.
Another thing is, like, suppose that your bias makes the expectation positive, where the reality is negative. So you could think your project is going to be successful, but when in reality it probably will not be. So expecting more money than you're actually going to get can be problematic in various ways.
Cool. Thank you.
I also have a question. Some papers introduce the risk aversion in the target to maximize for a news vendor. So, for instance, one may wish to maximize the mean variance criterion applied to news vendor profits as opposed to just the expectation. And the rationality of this is that whenever one may choose for a operational control that slightly increases the expected level of revenues, this might entail a huge increase of variance. And so one should actually trade off the two. Now, my question is, do you think it would be possible to extend or even apply the methodology that you have developed in this paper to analyze the naive estimation of a mean variance target, which is expected values minus lambda times the variance? I don't know if this is if this estimator is biased. I think so. I think the naive estimator of this is biased. And yeah, so that's the point. Because after all, the variance is an expectation. So it's an expectation of a profit minus the expectation of the deviation of profits from the expectation, right?
Yeah.
So maybe, I mean, at a modest cost, your methodology can solve this problem as well.
So I agree that that proposal makes a lot of sense, and that's what should probably be done in practice rather than just like a narrow expectation. To answer your question, our results cannot immediately be applied to that situation because a lot of our derivations are based on the form of the expectation, the expected profit. That's not to say that it can't be done. So we can change the objective instead of just having the expectation minus multiple times the variance. So at the end of the day, yeah, so that's a different objective. It might be possible. It will probably be a whole other paper because, like, actually, even though it's presented somewhat simply, we needed about 15 pages of math to derive all this. And if you're changing the form of the expression, you probably need another separate 20 pages of math. So it might be possible if it's not directly applicable. So we can't take what we have here and immediately get the answer in that situation. But with a lot of work, it might be possible.
Okay.
That's actually a decent idea for future research, but it won't work right now.
Okay. Okay, thank you very much, Michael, and thanks to all the participants. Now, before saying you goodbye, just a quick information. The next webinar takes place on Tuesday, March 19 at noon time, Paris time zone. However, it will not be, it will be broadcasted through Zoom. Despite that, the webinar will take place live in our Singaporean campus, because our speaker there will be Onur Boyabatli from the Singapore Management University. He will present a paper on stochastic capacity investment in the presence of production resource disruption and its implications for hedging. Again, thanks to all of you, wherever you are, and have a good day, a good afternoon, or just good night. Cheers.
Thank you, Andrea.
Thank you.